Hi everyone, in this video I'm hoping to give you some insight into the practice that some professional economists use to predict GDP before it's published. This is a technique known as nowcasting. So right now in mid-2026, nobody actually knows how the Australian economy performed last quarter. The official GDP figure published by the Australian Bureau of Statistics won't be released until 9 weeks after the quarter ends. But the Reserve Bank, our central bank, still has to make decisions about how interest rates are set based on where the economy is right now. Fortunately, other economic indicators are released much sooner, giving economists a way to estimate GDP before the official figure arrives. This is known as nowcasting, and it's the practice I'll be exploring here. So before any calculations are done or any modeling is performed, first we need to get data to input into those calculations. So for this model, I've decided to include the economic indicators of employment, unemployment, hours worked, building approvals, household spending, and goods exports. A professional model might choose to include more indicators, but this is what I've gone with for the purpose of my project. I then get this data for each indicator into my model using a Python package called read ABS, which pulls the data that I want from the ABS and prevents me from having to manually go through spreadsheets. And some of the code that you can see on screen gives you a rough idea of what was involved in practice in programming to pull the data for each of these variables. So how do we actually get GDP predictions from this data? Well, starting off, the simplest model we can consider is a random walk. This model simply follows the rule in my project that the quarter of GDP we want to nowcast is equal to last quarter's GDP. Another benchmark is the AR, auto regression model, which still only uses GDP data and is essentially a regression of current GDP growth levels on its past values. And I have also included an average of GDP over every quarter and a rolling average of GDP, which is just the average of GDP figures from the last 10 years. You might be thinking models such as these sound too dumb to consider. However, it's important that we have a baseline to compare our more complex models with, since sometimes complex models fail to outperform the simple ones. Okay, so now let's consider the bridge model, which is slightly more complex. Immediately when we look at trying to nowcast quarterly GDP, we hit a frequency problem because lots of the other indicators that we are using are monthly, while we need a quarterly estimate of GDP. So the bridge model helps overcome this issue. This involves averaging all monthly indicators within each quarter, and then regressing GDP growth on that quarterly indicator that comes from the average. This gives us a line of best fit, which we can then plug this quarter's partial GDP into the line of best fit, which will give us the nowcast GDP estimate. This process is repeated on each of our indicators individually, which we can then average to get our overall GDP nowcast based on the bridge equation for each indicator. This is calculated on a rolling window, meaning that we only use the last 10 years of data in each bridge calculation for a given variable or indicator. So what does this actually look like to build? The whole thing is written in Python, which has become the default language for this kind of work in central banks and finance alike. And while I can't explain everything that's happening here in the code in this video, I hope it gives you some idea to the practical side of building models like this. Basically, the bridge equations and the simpler benchmarks I mentioned previously are being built using a Python library called statsmodels, which is aimed squarely at econometrics and time series type work. So a bridge equation is really just a regression from statsmodels fit on my indicators. But again, we can consider an even more complicated model called the dynamic factor model. Here's the key intuition behind this model. Employment, exports, building approvals are all noisy reflections of one underlying thing that we want to know about, the business cycle. A dynamic factor model assumes a small number of latent factors drive the co-movement of many time series. Instead of reading each indicator separately, the dynamic factor model estimates that hidden common factor directly and strips out the noise. The actual calculation uses something called a Kalman filter, which I'm not going to derive here, but it is just implemented using stats models, as I mentioned. And this is not a niche model or estimation method. Many professionals use it in industry. For example, the New York Fed staff Nowcast has been nowcasting US GDP growth since April 2016 using this method. So once again, here's some of the Python code used to create the dynamic factor model. Like I said, the factor mostly comes from stats models. I didn't have to hard code the statistical machinery myself. I specify the model, hand it my indicators, and it does the estimation. And that's the reality of a lot of modern applied work. You're standing on top of well-tested libraries, and the skill is using them correctly, not having to reinvent them. So I ran back tests in a horse race style with every model mentioned, comparing predictions that each model would have made at each quarter in the past, only using the data that would have been available at that point in time, and then comparing these predictions to the actual GDP results from each past quarter. As you can see, the simple bridge average 1, and so the top of the dashboard showing my results has the simple bridge as the nowcast prediction. Notably, the sophisticated dynamic factor model did not beat the bridge average model. Why might this be? Well, GDP nowcasting in Australia is data poor. There's only roughly 130 usable quarters of GDP data for this model. And flexible models have many parameters. With little data, they fit noise. This is called the bias variance trade-off. So in our case, even the best model only beat our rolling mean benchmark slightly, and not by a statistically significant margin. So the honest scientific conclusion from this project is that Australian GDP is hard to nowcast at any given quarter. However, I would note that the results from my project are not universal, and that in some studies the dynamic factor model does outperform all of the other models you can see on screen right now. So I hope this video has given you a bit of a feel for the type of work that real life economists in central banks might be doing, getting messy data, dating it correctly, running the models, testing honestly, and producing a GDP nowcast figure that someone could actually use. And if anyone is interested, I'll leave a link to this live dashboard of my project, and we can see how the model nowcast prediction progresses over time.